Hi everyone. So I want to do a little bit more asynchronous content, so I'm going to post the beginning of this lecture for you to watch on your own time. So this is basically we're going to apply the things that we've learned so far to forces and 3D vectors and talk about using that to do some physics. So the topic of this lecture is forces in equilibrium, and it's some of the sections from Hibbler. So we want to talk about now, how do I use the tools that we have for representing vectors in order to solve some physics problems of objects in equilibrium. Okay. The purpose of this lecture is that you're going to have some more practice identifying forces. So we talked about how to identify the forces acting on an object in the last lecture. And then I'm going to teach you the principle of what must be true about the forces if the object is in equilibrium. And that is something which is called Newton's second law, which is possibly the most important equation in the course. And so this will be the first time that we encounter it, but we will encounter it many more times before the semester is over. And then we're going to use this problem-solving strategy to address both 2D and 3D problems. So I'm going to do 2D problems in this kind of pre-recorded lecture, and then we'll do some 3D problems live. Okay, so here it is, the most important equation in the course, possibly. There's maybe one other one, which are the top two. It's either this one or conservation of energy. Those are the two most important equations. So this is Isaac Newton in the top right there. Neil deGrasse Tyson calls him my man, Isaac Newton, and I agree. He's the one who's really set down all of the laws of mechanics that we are still using today. And this is Newton's second law, and you're going to ask, well, why don't we talk about the first law first? Because in my opinion, this is the most important one, so it's worth spending the most time on it. So Newton's second law, here it is in all its glory. F equals ma, which you've probably heard before. The thing on the left means the net force on an object. Okay, so there's a big summation there. That big summation means add up all the forces on the object. So this means add up all the forces that on the object. I find the net force, or the result of all of those forces acting on the object. When I do that, add up all the forces on the object, it's going to be equal to the mass of the object times its acceleration. Okay, and maybe we haven't talked about what acceleration is, but we will a bit later. So I'm just putting this here at least for your reference. So the net force in an object is equal to its mass times its acceleration. And what does it mean by the net force? It means I take all the force vectors acting on the object and add them up using the rules of vector addition. So notice that this is a vector equation. There's an arrow on top of the F and an arrow on top of the A. So when I add up all the forces, I have to add them using the rules for adding up vectors. All right, now what I want to focus on today in this lecture is objects which are not accelerating, so objects which are in equilibrium. So equilibrium is an object which is basically just sitting there. It's at rest, it's kind of stable, it's not moving, and it's not moving for a long time. It's not just like it's not moving for an instant, it's moving, it's stable, it's just sitting there for a long time. For example, if I put a book on the table, that book is just going to sit there and it's in equilibrium. So everything that's not moving around you is in some kind of equilibrium. So when objects are in equilibrium, their acceleration is zero. So that means they're not accelerating, obviously. And so they're just sitting there in equilibrium. And then the right-hand side of Newton's second law is equal to zero because the acceleration is zero. So that means that all of the forces added up on the object have to add to zero. In other words, all of the forces in the x direction have to cancel out to zero. All of the forces in the y direction have to cancel out to zero. All the forces in the z direction have to cancel out to zero. Now, let me just make a point that just be very clear that this equation, adding up all the forces equal to zero, is only true if the object is in equilibrium. If the object is accelerating, which we'll come to in a couple weeks, then you can't add up, then the forces are not balanced, they don't add to zero, they add to ma, right? They equal to ma. So just remember that when we come back to objects which are accelerating, you got to go back to F equals ma. For today, we're going to focus on objects which aren't accelerating, and so then the sum of the forces is equal to zero. Just to reiterate what I said on the previous slide, what does this mean? So if I have an equation which has an arrow on top of it, remember that's a vector equation, and a vector has components. That equation is actually code for 3 different equations. So there's one equation for the x component, one equation for the y component, one equation for the z component. So when you see an equation which has a vector arrow on it, you can remind yourself that that's really just like shorthand or code for 3 equations. And so those 3 equations are that the x components have to add to 0, the y components have to add to 0, and the z components have to add to 0. So that means if I add up all the forces in the x direction on the object, it adds to 0. Same thing for the y direction, same thing for the z direction. Okay. So now that's basically it. That's the whole lecture right there. Just add up all the forces. They must add to 0 in x, y, and z directions. But of course there's a lot of extra details in there when it comes to solving problems. And here's the steps that I'd like you to go through in order to solve these kinds of problems. So the first step is always to draw a picture, and that's basically true of any problem that you encounter in physics or in other disciplines as well. So draw a picture. In this case, we want to draw a free body diagram. We want to figure out what forces are acting on the object of interest. And then to help you with that, go back to the previous lecture where we talked about how to identify forces, just gravity and forces from things that are touching the object. Second step, pick a coordinate system. So you got to decide which way is going to be positive, which ways are going to be negative. And that will help you with the signs in your equations. So this is up to you. You can choose your coordinate system however you like. Your final answer will not depend on the one that you choose. And basically, everybody will agree on the physical result, but you have to make a choice and stick to it. Then I break the forces into components. So I break some of the forces into their x and y components, or all of the forces into their x and y components. And then I add up all the forces in the x direction and set it equal to 0. Add up all the forces in the y direction, set it equal to 0. And if I'm doing a 3D problem, I have to do it the third time, add up all the forces in the z direction, set it equal to 0. These steps 1 to 5 here, this is physics. Okay, this is the physics part, adding up all the forces, setting them equal to 0. The last step is where you have to solve the equations so you've set up the equations. Step 1 to 5 is getting the equations in front of you. That's all of the physics. Step 6 is a math problem. So once you've got the equations, you have to solve those equations for the variable you're looking for. Then at that point, the physics is done and you're just doing math. Okay, so the last step is a math problem. So you have to solve the equations, plug in the numbers last, check the units. Okay, so here's an example I'm going to illustrate for you of using this problem-solving strategy. Now, this is a very easy problem-solving strategy, so I will. You're going to say, I can do this really, really simply, but I'm doing it to show you how I want you to solve the problems. Okay. Okay, so here we go. Let's just read over the problem very quickly. So you're trying to have some fun in winter. Winter is coming by pulling your brother in a sled. However, he's gained some weight. The combined weight of the brother and sled is 80 kilograms. So I'm circling the things I know. You're pulling on a rope tied to the sled with a force of 800 newtons. And the rope makes an angle of 30 degrees with the horizontal. So those are the 3 things I'm given. Part A. Let's focus on part A. Whoops. Let's focus on part A. What's the frictional force acting on the sled? All right, so what's step 1? Step 1 is draw a picture. So I'm going to start by drawing a picture. So there we go. I sort of drew a cartoon there of the sled being pulled with the rope and the person pulling the rope there. So this step 1 is draw a picture, and then we need to think about the forces acting. So what is the object of interest? The object of interest is the brother plus the sled. So I'm going to think about all the forces acting on that object only. Okay, what are the forces acting on that object? Well, what's touching the object? There's the ground. So the ground exerts a normal force here. So we'll call that normal force. The ground also exerts a frictional force, which is holding him backwards. In this case, it is a static frictional force. Holding him backwards, even though the older brother is pulling, but not able to move him. Then we've got a tension force, which is because the rope is attached here. There's a tension force here. And we also have gravity, which is the weight of the person acting downwards. So I'll call this W. Okay. So we've got the weight of the person downward, normal force upward, static frictional force pointing to the left, tension force pointing to the up and to the right. Now the second step is to pick this, represent this whole object as a point. This point here is going to be denoting the brother plus the sled. So I'm simplifying my life. I'm making that point is all of the brother and the sled together is going to be represented by that point. And now I draw the forces acting on that, starting at that point. So I will have, when I transfer those forces over here, I've got static frictional force to the left, weight force downward, normal force upward, and tension force kind of up like this. Just like that. And this angle here is 30 degrees. And let's just call it theta, just to make my life easier. Like that. Okay, that's step one, draw the picture. Step two is pick a coordinate system. So I'm going to pick a coordinate system like this, plus x will be to the right, plus y will be upward. Let's go back and look. Okay, so what did we do? We did this part, drew a free body diagram, we chose a coordinate system. Now, if any of the forces do not lie on the xy axes, break them into components. So you can see I need to write down the components of each of those forces in the x direction and the y direction. And let me show you how I sort of, when you're starting out, a way to do that is to make a table. So this is going to be my force. This is going to be the x direction. This is going to be the y direction. All right, so I've got 4 forces there. So the first one's going to be the weight force. What do I have in the x direction? 0. What do I have in the y direction? Minus mg. Okay. Why is it minus? Because the direction, it's in the negative y direction. Okay, so I'm putting the signs in by hand. The weight force is in the negative y direction, so I put minus mg. Remember, g is a positive number, so I got to put that minus sign in by hand. Okay, what else do I have? Now I've got the normal force, upward. What do I have in the x direction? Nothing. What do I have the y direction? I'll put just the magnitude of the normal force. So the normal force, all of its magnitude is in the y direction. And it comes with a plus sign because it's acting in the positive y direction. Then we've got my static frictional force. In the x direction I have minus the magnitude of the static friction force, and then nothing in the y direction. Again, that minus sign is because this static friction force here is acting in the minus x direction. Okay. Remember, the thing in the absolute values here, absolute value Fs, that's the magnitude of the force. That's a positive number. So magnitude Fs is a positive number. I put the minus sign in by hand to denote the direction. And the last one is the tension force, which I have, that's the only one I have 2 components, one in the x and one in the y. So I'll have here the magnitude of the tension cosine of theta, and the magnitude of the tension times the sine of theta. Okay. So there's my table of all of the forces acting on this object. I've got static friction force acting in the negative x direction. I have the tension force acting in the positive x direction for its x component. And then I have, in the y direction, I have gravity downward, normal force upward, and the y component of tension. So I did this. Now, add up all the x components and set equal to 0. So all I have to do here for my x direction is I just add up all of the forces in the x direction and set it equal to 0. So all that means is I just add up all of the things in this column here and set it equal to 0. So what do I have? The first 2 terms are 0. I have minus the magnitude of the static friction force plus t cosine theta equals to 0. I added up all the forces in the x direction and set it equal to 0. Now in the y direction, do the same thing. Add up all the forces in the y direction, set it equal to 0. That means I take everything in this column, add them all up, and set it equal to 0. So what do I have? Minus mg plus the magnitude of the normal force plus t sine of theta is equal to 0. So those two equations, those are the equations of equilibrium, one for the x direction and one for the y direction. Okay? So at this point the physics is done. At this point we have done this step and this step. Okay? We've set up the equations of equilibrium by adding up all the forces in each direction. Now the last part is to find, to solve them and plug in numbers. Okay, so now let's see, for part A, what am I trying to find? What is the static friction force on the sled? So that is here. So I'm just going to solve equation 1. Let's call this 1 and this 2. So for part A, I'm going to solve equation 1 for the magnitude of the static friction force. Okay. So let's do it. I'm going to go to the next slide so you'll remember this equation. So solving for the static friction force magnitude, it's t cosine of theta. Plug in the numbers. Should be magnitude of the tension. So the magnitude of the tension is 800 newtons. The cosine of the angle theta is 30 degrees. Plugged in the numbers at the very last step. The units are okay because this is in newtons and this is a force, so it should be in newtons. And when I plug the numbers into this, I get 692.8 newtons. That's the magnitude of the static friction force. Now the question's a little bit vague. It just says, what is the force of friction? So what I'm doing here is I'm actually solving for the magnitude. But if you wanted to be really precise, you could say the static friction force is equal to minus 692.8 newtons I hat. Okay? And that was with this coordinate system that I chose this way, plus x plus y. So the magnitude is 692.8. The direction is in the negative x direction, according to the picture here. So you can see that this static friction force is pointing in the negative x direction, which is why I put a minus sign on the component there. Okay, now let's do B, and that's going to be the y direction. So I'm going to solve equation 2 for the normal force. So solve equation 2 for the normal force. And what do I have? So let me write it again. I had minus mg plus the magnitude of the normal force plus the magnitude of the tension force times sine of theta equals to 0. Solving for the normal force, I have the normal force is equal to mg minus the tension force magnitude times sine of theta. Plug in the numbers. Okay, mg, that's the weight. Should really say mass, right? So the mass, not the weight. So weight is a force, it should be measured in newtons, not in kilograms. So I will put in now the mass, which will be 80 kilograms, 9.8 meters per second squared, minus 800 newtons times the sine of 30 degrees. And you plug the numbers into that, and I got 384 newtons. Okay. That's the magnitude of the normal force. If you wanted to write it in a vector notation, you would write the normal force is 384 newtons, j hat. Okay. Just like that. Okay, so this is a simple example of solving an equilibrium problem using this problem-solving strategy. So what did I do? I just drew the free body diagram, made a table of the forces, added up all the forces in the x direction, set equal to 0, added up all the forces in the y direction, set it equal to 0. So to end here, I've got a couple of concept questions or clicker questions for you to practice on. So how about this example? 3 ropes, one red, one blue, one green. You can see them all there. So the red one on the left, blue one on the right, the green one pointing straight down. are attached to a metal ring and used to hang a box as shown. So for example, maybe you're going camping and you're hanging your food so you don't want the bears to get to it. You're using this to hang your food. Suppose I want to draw a free body diagram on the box. Which of the following, A, B, C, or D, is the correct diagram for the box? Go ahead and pause the video and see if you can decide which one of these is correct. So hopefully you've made a choice now. The most common mistake that students make here is they think it's this one. But remember, how do I decide what the forces are acting on the box? This is for the box itself. So I think about what is directly touching the box. And the only thing touching the box is that green string there, which is exerting a tension force upward. And that's it. And then there's gravity downward. So the correct answer to that one is A, because the only thing touching the box is the tension force upward. And the red rope and the blue rope do not touch the box, so they do not exert a force on the box. Okay? So the answer to that one is A. Now if I use the conditions of equilibrium on that box, it means that the upward tension force from the green rope must be equal to the downward force of gravity, mg. So that means that the tension force of gravity will be equal to the weight of the box, which is hopefully not surprising if the box is in equilibrium. A little bit harder one with numbers. Now suppose I give you the mass of the box and the angle is 15 degrees. The long cables have the same tension. What is the tension in the red rope? So as a hint, draw a free body diagram for the point P. So what I would like you to do here is pause the video, take out a piece of paper, try to work this one out. And if you don't know where to start, go back and you do these steps. So draw a free body diagram, choose the coordinate system, break the forces into components, add up the forces in this table, and then set them equal to 0. Okay. So do you have an answer yet? Hopefully you've worked it out. At the point P, I'm drawing a free body diagram for the point P, so I have to think about what is touching that point. Well, I have each of the ropes. I have the red rope, the blue rope, and it was supposed to be a green rope, and somehow it became black, so that one would be green. Okay, once you do that, you'll realize that the x components of the forces are going to cancel out because the tension in the blue rope is the same as the tension in the red rope, and the angles are the same. And to figure out the actual tension, I should look at the y components. So it looks like this. This is the free body diagram. The red tension pointing up at this angle theta, the blue tension pointing up the other direction at the angle theta, the green tension pointing downward. And we said previously that the tension in the green rope is equal to mg. Okay. Adding up the x components tells me that the tension in the red rope has to be equal to the tension in the blue rope. Because the angles are equal, you see, right? If the angles were different, then the tensions would not be the same. But the angles are equal. The only way that the x components can cancel each other is if the magnitude of the tension is the same. Now what happens in the y direction? Let's add up the forces in the y direction. What do I have in the y direction? I've got the y component of the red force and the y component of the blue force, and those are actually the same. So I have the t red sine theta plus t blue sine theta minus the green tension is equal to 0. Okay. Now these two are the same because the tension, the magnitude of the tension is the same and the angle is the same. So that's just 2 times t red sine theta minus mg equals 0. So the red tension is equal to mg divided by 2 sine theta if you solve that. And when you plug in the numbers, you should get 94.7 newtons. So hopefully you got that answer. If you didn't get it, try to go back over it, do it again, and see if you can come up with that answer. Last question. How about this one? Just a simple yes or no question. Is it possible to tie the ropes tightly enough so that the ropes are exactly horizontal and the box is in equilibrium? Yes or no? Go ahead and pause the video and see if you can answer this one. So hopefully you've chosen one of these two answers. The correct answer to this one is no, because remember, for it to be in equilibrium, this point P, it means that all of the y components of the forces have to add to 0. Clearly there's a downward pointing force from that tension, but there's no upward pointing force anywhere, right? I have the horizontal force from the ropes left and right, but I have nothing upward to balance the downward force. If I can't balance the downward force, it's not going to be in equilibrium. So this is not possible, actually. There's always going to be some angle, some very small angle there, in order to keep the thing in equilibrium. And you can see it also from the formula which we derived previously. This was the formula for the tension in the red rope. In this case, theta is 0, because previously we had theta like this. If the rope was horizontal, theta would be 0. If I put 0 into this formula, I get sine of 0 is 0, and I get something which is infinite, which doesn't make any sense. So clearly, this diagram doesn't make any sense. So the answer is no. You cannot hang something completely horizontally like that in equilibrium. Okay, so I'm going to end it there, and then we'll pick it up here in class. We've talked so far about adding up forces in the x direction and the y direction, and now we just need to think about what if I add a third dimension there, the z direction. And the strategy is exactly the same, it's just you have to, the visualizing of the problems becomes a little more complex. So we'll try and practice that, problems like that in class. So thanks again for your attention, and I hope you found this lecture useful.